Sound vibrations leave compressions and rarefactions in the air. Now, those are terms that we have used with longitudinal waves, and we have a pretty good depiction here of longitudinal waves. Remember, those are kind of like the slinkies. Here we have an area of compression, here we have an area of rarefaction, and don't forget that you can in fact put that on a sine curve, kind of like you have right down here. So these are longitudinal waves. Sound waves are. They're longitudinal waves. Now these longitudinal waves cause your eardrum to vibrate, and we'll talk a little bit later about what happens from there. But it has to do with the speed of sound, what comes to your ear, or how quickly it comes to your ear. The speed of sound is roughly 760 miles per hour. Now I say roughly because that changes, for one thing, with temperature. Notice the air temperature being Celsius makes it 343 meters per second, which is roughly a little bit less than 760 miles per hour. But you notice whenever it's 0 degrees Celsius, that the total is a little bit lower, 331 meters per second. So the warmer the air, the higher the speed of sound. Now, you have speed of sound is different with other mediums. I think we have touched on this, the fact that solids will have a higher speed of sound than liquids will, which will have a higher speed of sound than gases will. Now, one thing this chart does not account for, there are some solids like rubber where the speed of sound is drastically lower, like 50 meters per second, and that's the stuff you can put in soundproof boosts to make those out of, to where you can really slow the sound down to like next to nothing. Well, anyway, the greater the amplitude, the louder the sound. You may remember what an amplitude is. It's the distance from the x-axis up to the crest and to the trough. It should be the same distance. So if you have a higher crest and a lower trough, then you are going to have that more sound, the louder the sound, I guess I should say. Now, a term that you often see when it comes to how loud things are is intensity. Now, intensity doesn't necessarily mean how loud it is in all circumstances. It means how loud it is relative to where you are next to that sound. If you're 2 miles away from a jet engine, you will not hear it near as loud as if you are 2 feet away from a jet engine. And so intensity and relative intensity kind of is measured through that. Now, we have a unit that relative intensity is measured in, and it's called decibels. Now, you probably heard of decibels. A no sound, well, we pick up no sound at 0 decibels, and our pain threshold is in the ballpark of 120 decibels. Now, sure, there are sounds which are louder than 120 decibels, but they're kind of that's about the point at which you might get pain if you really get a lot of exposure to that. Well, anyway, decibels are a little bit different than normal charts where you go from normal measurements where you go from like 0 to 120. You know, they're very similar to the pH scale that we recently studied. You know, in the pH scale, if you have something that's a pH of 4 and something that's a pH of 5, the pH of 5 is 10 times more, 10 times more acidic, I should say. The pH of 4 is 10 times more acidic than the pH of 5. We're getting into the logarithmic scale is what we're doing here. The Richter scale, you may remember from an earlier grade, is similar to that. So let me take a look at a chart over here as far as the decibel levels. You see here we have levels going up every 10. So it's kind of like the pH scale if you take the zeros off right here. Now, of course, you wouldn't say a whisper would be a 3. You would say it would be a 30. But you have 10 times the intensity every time you go up a level, like from 30 to 40. So a refrigerator would be about 10 times louder than the whisper, and the moderate rainfall would be about 10 times louder than the refrigerator, and so on. And you can see once you get up to 120, you truly are getting to some very loud sounds, each of which is 10 times louder than the sound that's at the previous level, like 130 is 10 times louder than 120, and so on. So that's a little bit about the decibel level. Now let's talk a little bit about pitch. Pitch, as you know, is like a high sound or a low sound. Whenever you have those higher sounds, it's when the number of vibrations are higher. You know, whenever you have like a sine curve, you have lots of vibrations, the faster the curve goes, or on the chart. And so that means the frequency is higher. So the higher the pitch, the higher the frequency. Now that's often made in smaller instruments. Like if you take a clarinet, you're going to have a higher pitch than, say, a bigger instrument like a tuba. Now a tuba and other things that make low pitches have fewer vibrations and therefore less frequency. Now humans here, you may remember the 20 to 20,000 hertz range. Now remember, hertz is in frequency, and there are some sounds that we just cannot hear just because we only hear in this kind of hertz range. Now below 20, those sounds are labeled as infrasound. If you get above 20,000, those sounds are labeled as ultrasounds. Now, we actually have some use for these ultrasounds, even though we can't hear them. For example, if you have a ship sonar, this particular ship probably is a fishing ship, and it uses sonar in which to find schools of fish and the bottom. This is actually a sound wave. Even though we cannot hear it, it is ultrasound. We cannot hear it. It's above 20,000. But it is useful for finding fish or finding parts on the bottom. Bats in nature, they emit sound waves to keep from running into each other and to keep from running into things. I'm sure you've studied that at some point in your career as a student, but that is a sound wave, and it's ultrasound because it's above 20,000. Also, sonograms used to create these computer images of babies in the womb. They're also sound waves. Now, these sonograms, they use like hertz of like 1 million hertz, even up to 15 million hertz. And that's an incredible frequency right there. But the reason they use that incredible high frequency is because the wavelength must be smaller than the smallest details. So if you're trying to find little bitty details like noses and fingers and toes, you have to really have a high frequency. Let's go to another slide. Hey, you know, we mentioned that we are in the 20 to 20,000 hertz range. What about other animals? Well, an elephant is 6 to 12,000 hertz. They don't hear a lot of things we hear, even though they're lower on the scale. Dogs, as you know, hear ultrasound. They hear things above what we can hear, like a dog whistle. 40 to 46,000, and dolphins, their decibel, or not decibel, but hertz range is 70 to 150,000. It's kind of a shows you that the animals, for the most part, have different ranges that they hear. Well, why don't we talk about musical instruments and sound? Musical instruments rely on standing waves. You may remember standing waves. We use the example of if somebody were holding a rope here that was tied to, let's see, I'll use a different color. If somebody were using a rope here that was tied to a wall, and they ended up shaking the rope up and down once, the wave starts going this way. And then as the wave is going and coming back, they shake the rope again. And they send another wave down to it, and they would inevitably meet, and they would create areas where you do not have any vibration. Those would be the nodes. You may remember the nodes. And you can see nodes right here, nodes right here, and so on and so on. And they had areas where there are vibrations, and that would be this area in between the nodes, and those are the antinodes. So how does that apply to like a musical instrument? Well, take a look up here. We have right here is where all the strings are tied. All the strings are tied right up at the top, and all the strings are tied right about here. So it's kind of like that rope that you send vibrations through, except it's not going to be near as loose. As you are picking these strings here, you're still creating areas of no vibration and areas of vibration. You're still creating antinodes and nodes. So that makes this standing waves. And that's going to be true for I think all the musical instruments. They are going to rely upon standing waves. Now, pitch can actually be changed on a standing wave by moving the shortening the lengths of the strings. For example, right here, if you put your finger on this string, what it basically does is shorten the length of the string. Instead of it being really long, it's kind of short. So that actually creates a higher pitch. Interesting. The primary standing wave on a vibrating string has a wavelength that's twice the length of a string. Now that really only kind of makes a difference in kind of creating a standard for what these instruments are supposed to sound like. And this standard is called the fundamental frequency. Now, the fundamental frequency is what tuning forks try to tune into. A tuning fork vibrates at the fundamental frequency. So you can then model tuning like a piano to what the tuning fork would declare would be the fundamental frequency. Now, some instruments can't seem to hit exactly that same frequency that the tuning fork can. And clarinet, for example, is one of those. Now, what I've done here, the actual notes it plays are kind of all around this sine curve, but not really right on this sine curve. But a clarinet just can't seem to hit it unless it has multiple notes that it is playing. So in some cases that just turns out to be the case where you just can't quite hit it. Now the term here is going to be harmonics. You have items like clarinets that emit whole number multiples, and that's kind of a long way of saying it can't seem to hit the notes, that the multiples are kind of on either side of the fundamental frequency. So instruments themselves give off vibrations, well, kind of like this guitar here. Not all the vibrations are going to come from the strings. You do have a little bit of vibration that comes from the wood up here on the handle, and a little bit of vibration that comes from the wood back here. Whenever you have those extra vibrations that are at the same frequency, you hit what's called resonance. And resonance just amplifies the sound a little bit. I think we have one more thing to show you. Vibrations hit the eardrum, and I'm not going to go into huge detail on this. I just don't think it's as pertinent to physics itself, but once it hits the eardrum, it goes through these three little, you have these three little bones right here, and then you have the cochlea. Now inside the cochlea is where you have another membrane that reflects the vibrations that hit the eardrum. Now this other membrane has hair cells near it, and these hair cells stimulate the nerve fibers here that send an impulse to the brain, and there the brain interprets the sound. Now that's kind of a basic way that the eardrum and the cochlea and the nerves work. Hope you've learned a little bit about sound waves.